Good morning. It's our last class today. Can you believe it? It's crazy. Crazy. Maybe you have classes on Monday, but it's our last class today. Last class today. What are we supposed to do on our Tuesday and Thursday mornings? We'll think of something. So we won't have time to review. Yes, sleep in. Yeah, we can manage, right? So we do have to finish inverse trig today. So what I'm going to do is I'm going to post a review document. I'm meeting with Steve either later today, just to kind of figure out what we should be doing, and then just because I'm doing the same thing with my pre-calcs as you guys. So so I'll post a review document. The test is going to be just a PDF that you do, and then you post your work, and so it's going to be very similar to the tests that we have been doing, but it's cumulative, right? So it's going to be the whole term with an emphasis on this new stuff. So not like a heavy emphasis, but you know, it hasn't been tested, so it's going to come up. But yeah, so when is our exam? Our exam's not till a little bit later, right? So what we can do is, oh yeah, we're not till the 16th actually. So we can probably set up a review day, which I'd record anyways, and just kind of, if you wanted to. Or we can all have office hours that I'll post too. So figure something out. But the final exam is on, I just had it, the 16th, which is what day? On Wednesday, December 16th, from 1 to 4. Oh yeah, so well, it does cover all the material, so definitely review things that you've been tested on already. Usually I put stuff on the test to prepare you for the final, so so definitely review the tests that we did, and just it's going to be on everything. But like I said, if I'll post that review document, so then you should have a pretty good idea of, you know, things you can skip and things you should focus on. Okay. So let's see here. Okay. It's on December 16th, and if there is interest, we can do a review day. Once classes are done, right? So even though this is our last class, we can still meet if there's a time that works for you guys. What's nice is you guys kind of move in blocks. So if there's a time when you want to have it, just let me know, and we can do that. Okay. And all right, so let's see here. I feel like there was something else I wanted to say, but if I didn't write it down, it doesn't stick. Okay, so last day, just for a little bit of review, last day we did, we kind of finished on SOHCAHTOA 2.0, if you want to think of it that way, right? We went beyond sine, cosine, and tangent, and we talked about, okay, well, what does cosecant look like? What does secant look like? What does cotangent look like? And so we introduced kind of SOHCAHTOA version 2.0. Right, so we had, I'll just grab it from here, I think. Right, we had these, so we have sine, cosine, tangent, that's SOHCAHTOA, but then we also said, okay, well, sine and then cosecant are kind of flipped, right? And secant, they're flipped of the cosine, and then cotangent is the flip of the tangent. And so this one we're going to use today. So that's why I'm introducing it again. Okay. And so this is kind of here, up here, you've got SOHCAHTOA, and then here, this is why I'm calling it 2.0, because we're just extending it a little bit to some more trig functions. Oops, that's not what I wanted to do. I wanted to go back in here. And, oh yeah, so, and then we talked about just solving triangles. Solving triangles just means that if you have the lengths of all three sides, then you can easily arrange all those trig functions for some angle theta. Right? So if we know the lengths of all three sides of a triangle, we can solve the triangle, which just means find all these 6 trig functions of theta, right? But if you know the opposite, the hypotenuse and the adjacent, then you can arrange all these trig functions really easily. So solve means find the 6 trig functions of theta. Now let me see. I wanted to show you because I posted, oh, not that one. I posted 2 optional formula sheets. Obviously, we're writing the test open book, so you don't really need a formula sheet per se, but maybe it's nice to have it all in one place. And so the first one is the Math 120. So this is the Precalculus formula sheet that they would usually get, so I don't see any harm in giving them to you. It's not very pretty, right? But all the information that we need is here. So here, some of these, we didn't actually spend too much time on trig identities. We didn't get that far, and that's okay. It's kind of one of those things. If you get to it, great. If you don't, then but we're going to use the Pythagorean theorem today, and we have in the past too, but not as much as we will today. And then here's SOHCAHTOA again, and here at the bottom is the transformation of the sine and cosine functions. So, and that's what we talked about last day when we had, okay, we need to find the amplitude, the period, and the horizontal shift, which is called the phase shift on here, but it's the same. The one that I'm more interested in is this trigonometry formula sheet, which is also labeled optional, of course. But what's nice about about this one is that full unit circle with each little point kind of blocked off, right? So this one has everything that we are going to talk about today and talked about last day, especially. And the only thing that we didn't cover is the laws of sines and cosines. It's on there, but just kind of block it from your view if you don't like it. Okay. So this one is kind of jam-packed with information, which is nice. All right, and I'm going to be referring to this unit circle because it's going to make our lives a little bit easier. Okie dokie. So I've pulled them in already, especially this little guy, right? So just remember, we haven't done the laws of sines and cosines. They're pretty fun. So you don't need to have a right angle triangle. You can just use the laws of sines and cosines, but we didn't get there. That's okay. So this one here, that's the one that I'm going to be referring to today. Okay. But also, I guess this here. Okay. All right. So let's see here. Where's my, there. Notice that all this is on that trigonometry formula sheet that I gave you, right? So that's nice to have it all scrunched together. All right. So what I want to do is I want to start our last section, which is on inverse trig functions, right? So you've probably seen on your formula sheet and maybe seen in the past sine to the -1, cos to the -1. So those are the inverse of the inverse trig functions. Inverse trigonometric functions. And I posted the handout separately because I wasn't sure if we'd get here, but then if we can do the inverse trig, it's kind of important, so that's why we're doing it. All right, so we've talked about inverse functions before, right? So one thing that we know already is that for a function to have an inverse, it has to be 1-to-1, right? So we remember that in order for a function to have an inverse, it needs to be 1-to-1. One way that you can check it, well, you can check it kind of mathematically with a proof, right? If f of a equals f of b, if you force them to be equal to each other, then a equals b should be what falls out. That's hard to do for trig functions. So instead, we're going to use the, we can check it graphically, right? We can see if a function is 1-to-1. A function is 1-to-1 if it passes the horizontal line test, right? A function, so a graph is a function if it passes the vertical line test, right? I can only cross the graph at one point for each vertical line that I draw. And then a function is 1-to-1 if I draw horizontal lines and I only cross the graph once. So a function is 1-to-1 if it passes the horizontal line test which says that any horizontal line can only pass through the graph once. So any horizontal line can only pass through the graph once. Okay, that's a problem, right? Because we know from last day, we know that sine starts here at 0, 0, and then it kind of goes up to 1, and then down, and then up, and it just kind of keeps going and going. Oh, that didn't look very good, right? But it just keeps going, and it does the same thing on this side, right? So when I try to draw a horizontal line here, that's bad news, right? So here, this does not pass the horizontal line test. Okay, but we have, so this is sine, let's label it. So this is the sine of x, okay? But we have inverse sine buttons. So what happens is we say, okay, well, what if we restrict the domain for sine, right? So what we do is we say, okay, well, on what section, right, kind of close to the origin, because that's where we're starting, on what section can we make this thing 1-to-1 and still have a good representation of all the different y values? So if you start here at 0, 0 and you go and do kind of like this, right? In order to cover all your y values, right, from +1 to -1, you would actually have to go through this kind of hump and then down. So that's not very good, because this is where it doesn't pass the horizontal line test. And then the next hump, it wouldn't pass it again, right? So what we do is we restrict the domain, and we only look between -π/2 and π/2. Okay? So now if I kind of focus my attention on -π/2 and π/2, now here it passes the horizontal line test. So in this little region, we restrict the domain in order for it to have an inverse, right? So to find the inverse function of sine of x, we restrict the domain to -π/2 π/2, so that it passes the horizontal line test, so that sine of x passes the horizontal line test. Okay. We do the same thing for cosine, right? And so for cosine, let's draw. We know cosine starts at 0, 1, right? So maybe up here. And then it goes down to something like that, and on the other side as well, right? So here you've got the cosine of x. Okay. So again, it doesn't pass the horizontal line test, right? I didn't draw it very nice, but this wave, this cosine wave, keeps going to -infinity and +infinity, right? And so it would definitely not pass the horizontal line test, because it would just keep intersecting. But we also need to represent the range of our y values, right, from +1 to -1. And so, or -1 to +1, doesn't matter. So if I did the same negative pi over 2 to pi over 2, I'm still not passing the horizontal line test. So what happens is I need to restrict the domain for cosine, but a different domain. So what I do is I go from 0, 0 here, or from 0, and then I go out to pi. Okay. So here, we restrict the domain from 0 to pi. We restrict the domain of the cosine of x to 0 to pi, inclusive of those points. We haven't looked at the graph of tan of x, but let's have a look here. If we go to Desmos, oh yeah, I was just kind of playing around here. But let's focus on, I'm going to delete sine of x, cosine of x. Okay, so here, this dark blue one, or I guess it's maybe hard to see. So sine inverse of x. Maybe I should add those functions. No, it's okay. So the blue one is the inverse sine of x. So we said sine of x, we saw sine of x here. We said, okay, we're only going to look at this section. The inverse, we flip on the y equals x line, right? So the inverse becomes something like this, where you've got this kind of curve up and down, right? So it's just been flipped on the y equals x line. Same thing with the inverse cosine. Looks a little bit weird, but that's what it looks like. And then I'm going to remove these, and just have a look at the tan of x. Okay, so tan of x actually has all these vertical asymptotes, just keeps going and going and going and going. And so what we do is we restrict it to just that middle line here. Right, so we only look at this one and we only consider that one. And so when I look at the tan inverse of x, it ends up looking like this, right? So it's just flipped on the y equals x axis, and we're only looking at this kind of middle one, right? We restricted our domain to be negative pi over 2 to pi over 2, not including those endpoints. And then to find the inverse, we just flip it. But notice that the inverse is this nice kind of kind of continuous function, right? So it has these horizontal asymptotes, but it's just kind of nice and clean looking because it keeps going and going, unlike sine and cosine, which are just little blips. Right? So let's go. So I posted the 6.4 lecture notes. So here we have this restricted domain summary. Right. So the tan of x, notice that it doesn't include those endpoints, right? And we do have to keep in mind that, okay, the sine of x and the cosine of x, their domains are going to be, or y, it doesn't actually matter. We're restricting the domains to different areas, right? And then here, the tan of y or x is the same as sine, but not including those endpoints. So inverse trig functions behave like this. Okay. So we've found things like x is the cosine of the angle and sine is the y of the angle. So if we're working on a unit circle, right, we've got x, y coordinates, which means we know sine and cosine. And so now what we're going to do is we're going to read these as, oh, this got confusing, didn't it? This y and x are not actually the x, y coordinates. Ugh, yikes. I guess I should have written them the opposite. That's okay. We'll keep that one, but I'll flush it out. First, I want to bring in this little box so that we can talk about what is going on here. So I'm going to delete this one here. Okay. So like we said, right, if we're talking about the inverse of the function, we do a little power of -1. And so what we have is we have the domain of the inverse of the function. And then the range becomes that restricted domain. So notice that this is the restricted. Notice the range is the restricted domain of the original function, right? So by that I mean, for the sine inverse, I mean sine as the original function. Okay. Just as a heads up, you can say sine inverse, cos inverse, tan inverse. Sometimes we call them arcsine, arccosine, and arctangent. Just keep an eye out for those. They mean the same thing. They're both referring to the inverse. Okay, so here I'll just kind of highlight that, just some terminology, right? But here, read sine inverse, right? Or if you want inverse sine. So the -1 you read as the inverse. So inverse sine or sine inverse. Okay. Or if you prefer, you can say arcsine, arccosine, and arctangent. That's fine. Okay. All right. So what happens is if we have some inverse trig function of some value, well, what that's saying is that, okay, the sine of some angle is equal to 1. Okay, so what is that angle? So we use these inverse sines, inverse cosine, we use these inverse trig functions to find the angle that gives us the value. Okay. We use inverse trig functions to find the angle that yields a specific value. A specific value of x, y, or y over x, right? Because cosine, and I'm going to start using theta, right? So an angle theta, feeling really confident that we talked about theta last day, hopefully, but theta is just an angle, right? So the cosine of theta, theta represents an angle. Theta is an angle, right? Just kind of a variable for an angle. So the cosine of theta is going to be x on or from the terminal point, from P of xy, if Pxy is the terminal point. Okay. Same thing with the sine of theta equals y, right, from P of xy. Okay. So the sine of theta, so the sine of some angle is going to be the y coordinate on from the terminal point. And tan theta will focus on these three. Okay. Tan theta is going to be y over x as long as x is not equal to 0, right? Which means that the terminal point can't be at x equals 0, right? So you can't be on the y-axis. Okay. What we'll find is that finding the inverse tan of something is going to be a little bit more work just because it has this combination of y and x, right? So y over x. So sometimes we have to put in a little bit of work to figure out, okay, what combination of y and x coordinates is going to give me the value that I need. Now, notice, okay, that if you have sine theta equals y, right, where the y is from P of xy, I want to emphasize when it's from the terminal point and when it's not from the terminal point. For the most part, I'm going to just try to use x and y. That's why I deleted that one little box, because it's not clear that it's not from the terminal point. So, but what we have, right, when I take the inverse sign, I can actually just move it over to this side, right? So thinking back to how we found the inverse before, it's similar, right? But it's a little bit weird because the sign, we just use it as one function. So what we have is that theta must be equal to the inverse sine of y. Okay, so what you can do is you can say, okay, well, what angle, if you have to solve sine inverse of y, right? So some number y, what angle gives me a terminal point of y that's given here. Okay, so let's do some of those examples to show you what I mean. Start nice and slow on 5. Okay. So if we want to find, and you don't want to just use your calculator, that's no fun, right? Of course you can use your calculator to check your work, but I'll expect to see the work that you do, and so some of these require more work than others, but just kind of explain to me how you're finding these, right? So let's do 5a. Sine inverse of 1. Okay, so now we're saying, okay, sine inverse of 1. So the terminal value of y is 1. What angle made that happen? Okay, so I'm just going to write that here. Oops. This is essentially asking you to find what value, or sorry, what angle yields a terminal point x1, okay, because the sine, right, is your y. Okay. So here, sine of x equals 1. Okay. Or sine of theta if you prefer. Here. I'll use theta now. We're ready. Sine of theta equals 1. And so now I'm trying to find theta. So all I've done is I've moved over the sine, right? I've taken the inverse sine of 1, which leaves me with just theta. So sine theta of 1, all I'm really finding is, okay, well, looking back to our unit circle, and let's grab it in here. So now I want to know, okay, what angle yields a terminal point with a y value of 1? Well, there's only one of those points, right? And then the other thing I want to make sure is that, remember that the sine, the domain for sine has been restricted to negative pi over 2 to pi over 2. Luckily, this is still in the restricted domain, right? So we'll want to make sure that we're working between negative pi over 2 and pi over 2, right? So on this side for sine, and then from 0 to pi for cosine, and then excluding the endpoints for the inverse tan. Okay, but we'll go through examples. So here, right, we see that this is the only place where y equals 1, right? And so the angle that makes this happen, right? So theta is going to be pi over 2. Okay. So we say, you know what? We say sine inverse of 1 is equal to theta, right? And theta must be pi over 2 from the unit circle. And you can try it on your calculator, right? Just make sure you're in radian mode because we're not talking degrees here, we're talking radians. And so the inverse sine, you have to go shift sine of 1. And these calculators are so nice because they actually give you the exact answer, which is pi over 2. Most calculators don't do that. They give you some nasty decimal approximation. Then you have to kind of figure out what it is in terms of radians, pies, etc. So that was 5a. We're going to do the same thing for cosine, but just remember that cosine is actually the x value on the terminal point. And so cos inverse of 0, all right, equals theta. Solve for theta, right? So what angle gives a terminal value of x equals 0? Okay. So what angle theta gives a terminal point 0y? Right, because the cosine, cos theta equals 0. Okay. So now we go back and we look at our unit circle, right? And so we've actually got two options now. Here at 0, 1, Okay, and then the next time it happens is on the other y-axis here, 0, -1. But remember, for cosine, we restricted our domain to be between 0 and pi, right? So let's see here. Cos theta equals 0 at theta equals pi over 2 and 3 pi over 2. Pi over 2 and theta equals 3 pi over 2 on the unit circle. But we have restricted the domain to 0 pi inclusive. So theta must be pi over 2. Okay. Okay. Not bad. What if we have to do the inverse tan of root 3? Okay. So we remember root 3 has kind of come up, root 3 over 2, root 3 over 2. I've got different versions of root 3 over 2 here, positive, negative. So we remember that the tan, so the tangent, is restricted to from pi over 2 to negative pi over 2 or vice versa, not including those endpoints. So we need to find some angle between on this kind of right-hand side of the unit circle that gives me y over x is equal to root 3. So let's write that down. So we've got the inverse tan of root 3 equals theta. Okay. So here, what we need to find is, recall from the terminal point pxy, tan theta is y over x as long as x is not equal to 0. Okay. So we need to find some coordinate xy that's going to reduce to, so when I take y over x, I need it to reduce to root 3. So we need to find a terminal point which reduces y over x to root 3. Okay. And remembering that the restricted domain we can only use our restricted domain which is from negative pi over 2 to pi over 2, not including those endpoints. Okay. I've got some pretty solid candidates, right? Root 3, I know I need to have a root 3. So I'm going to look at what are my options for root 3 here. So I've got just starting here at the top of the circle maybe, and knowing that I can only go on this right-hand side. So what I'm going to do is I'm going to have, okay, I've got a y equals root 3 over 2. Okay. And root 3 over 2 is my y, and then 1 over 2 is my x. So I can just quickly in my head, root 3 over 2, 1 over 2, flip and multiply. What do you know, right? It works out. So we'll see one that's a little bit harder. Obviously, we're just starting So, right, the other option would have been root 3 over 2 as my x and 1 over 2 as my y. Okay, so if I did 1 over 2 root 3 over 2 and I flipped these and multiplied, I'd get 1 over root 3. So that's not the angle that I'm looking for. Here in quadrant 2, I'm dealing with some negatives that I won't be able to shake because only one of these values is negative. So for that reason, I knew I had to be up here in the first quadrant, right? And it just so happened that the first one I look at is the one that works. Okay. So what we're going to do is try, what was it, 1/2 root 3 over 2. Okay. So I'm going to do y over x is root 3 over 2 over 1/2. I've got a fraction over a fraction. So I've got root 3 over 2 times 2 over 1. Flip and multiply. We should be really good with working with fractions. I know you are. So now this 2 over 2 cancels. And I'm left with root 3. Okay. This corresponds to, so this terminal point that I ended up using and it worked, right? We checked some of them before, so we knew this one was going to work, right? This terminal point is attached to an angle of pi over 3. Okay? So the angle that made this happen is pi over 3. So the angle that gives one-half root 3 over 2 as its terminal point is pi over 3. So what we can say is the tan inverse of root 3 is pi over 3. I always write my tans weird. Looks like tar. But anyways, I'm not going to change it because that's how it always ends up looking. Let's do another one. Let's do a little bit of a harder one. Let's do number 8 here. Okay. In fact, I'm going to steal it down. Copy. So I have it. So 8a. Now I've got the sine inverse of negative root 3 over 2. So remembering that, okay, the only way to get negatives is if I go into that lower quadrant. Remember for sine and tangent, so sine and tangent were restricted to the right half of the unit circle, and for cosine we're restricted to the top half. And so here, if I need my y value to be negative root 3 over 2, right, because sine is attached to my y value, and I'm going to just grab this here. So I don't have to scroll so much. Oops. Okay. So I need my y value to be negative root 3 over 2, and I'm restricted to be between pi over 2 and negative pi over 2, or vice versa, right? Technically, you should go from negative to positive. So negative pi over 2 to pi over 2. Notice though, okay, so I found my value, right? I found the angle that's going to make that happen. But here it's called 5 pi over 3. 5 pi over 3 is not actually between negative pi over 2 and pi over 2, right? Because negative pi over 2, you've just gone clockwise, right? And positive pi over 2 is up here. So if we're restricting it like that, then what I need to do is I need to convert this 5 pi over 3 to a negative angle, okay? All that says is I need to go negative pi over 3, right? Because I need to go clockwise to pi over 3. So here we find it, this is our negative root 3 over 2. Okay. Sine inverse of negative root 3 over 2 is theta, and theta is 5 pi over 3. But on the restricted domain, we say theta is negative pi over 3 instead. Okay. Because you're going to move down to pi over 3. Notice that I know that it's going to be pi over 3. Well, one, because it's over 3, but also because this point is negative pi over 6, this point's negative pi over 4, and this point's negative pi over 3, because I'm just replicating what happened up here in the first quadrant, just flipping it on the x-axis. Let's do the same thing for the inverse cosine. Inverse cos of negative 1/2. Okay, so again, no, I'm gonna delete that. I need an x value of negative 1/2. Remember cosine is restricted to this top half, right? So that makes a difference, because if we were restricted to this side, again, there is no negative x value, right? So that doesn't work. But because we're working on this top half, now I'm looking for an x value of negative 1/2. Looks like I found it here and only here at 2 pi over 3. Okay. So we say this is equal to theta. I actually find it easier if you just let it equal theta. So it looks like you're solving for something. And then, so cos theta equals negative 1/2. Theta must be, what did we say here? Oops, underline the wrong one. 2 pi over 3. From the unit circle, right? So once we get more comfortable, right, we can just say that it's from the unit circle. That's fine. You always just want to make sure that it is in the restricted domain, which it is. 2 pi over 3 is between 0 and pi, so that's good. Okay. Let's do tan inverse of negative root 3. So in order to get a negative value, right, I need to be in that fourth quadrant, right? So tan, I'm restricted to this right-hand side of the unit circle, right? But I need to have one of these values as negative, right? It doesn't matter which one, but I also need it to reduce when I do y over x. I need it to reduce to root 3. So it's just a matter of kind of cherry picking here values. So y over x, root 3 over 2 over 1/2, we already did it, right? And we know that it works out to root 3. And so here, at theta equals 5 pi over 3, which we already actually worked on, right? 5 pi over 3, which is negative pi over 3. At theta equals 5 pi over 3, oops. Or theta is negative pi over 3. P of xy is 1/2 negative root 3 over 2. Oops. Positive 1/2. X is positive. Negative root 3 over 2. So tan theta is y over x, where I'm pulling my x from here and this is my y. So I get negative root 3 over 2 divided by 1/2. Again, I'm just going to flip and multiply. I've already done this math, right? Negative root 3 over 2 times 2 over 1. These 2's cancel, and I'm left with negative root 3 over 1, which I'm just going to write as negative root 3. So that means that this is the theta that I want, 5 pi over 3, but I'm restricted on the domain, so I have to convert it to a negative angle, negative pi over 3. So, which checks out, therefore, theta is negative pi over 3. So the tan ones are a little bit harder, right? Because you have to do a combination of x and y. But if you're negative, right? So if your angle gives you a negative value, then you have to end up down here in this quadrant somewhere, in this fourth quadrant, because this is where one of your values is negative, so that's your only option. Now, then you have to say, okay, I'm going to convert this 11 pi over 6 to negative pi over 6, negative pi over 4, and negative pi over 3, right? So what I'll do here, maybe I'll copy this and just kind of put it here. Keep it on the same page. So what happens is that this way you're at negative pi over 6, negative pi over 4. I should make it bigger. It doesn't really work. Put it on the next page. Whee! Why not? So here, this is negative pi over 6. To this point, it's negative pi over 4. And to this last point, right, you're at negative pi over 3. Right. So these you would convert to negative angles. In fact, if you want, you can replace them on here with negative pi over 6, negative pi over 4, and negative pi over 3. And that might be nice. Right. Okay. So let's see here. Pretty well, the last thing we're going to do is just composing trig functions, and it's going to look nasty, but using the Pythagorean theorem, we're actually able to make it look quite nice. So, oops, not that one. 6.4. So what we're going to do is, if we have some triangle like this, we'll be able to find the inverse sine, the inverse cosine, and the inverse tangent of theta. Sorry, not of theta. Theta is the angle. Okay? And so if I want the inverse sine of this, well, all I'm going to do is remember that sine is opposite over hypotenuse, right? So sine theta is the opposite over hypotenuse. Okay? So that means that the sine inverse of some number is equal to theta. Well, all I'm looking for is the opposite over hypotenuse, right? So if I map this back, right, then you can see that theta is the sine inverse of the opposite over hypotenuse, which you can easily find, right? If you have theta here, then the opposite is 8 and the hypotenuse is 10. So this value here is going to be 8 over 10. Not bad. How about the cosine? Well, cosine is adjacent over hypotenuse, right? And so the adjacent to theta is 6 and the hypotenuse is 10, 6 over 10. The tan, opposite over adjacent, opposite over adjacent. So it's just using SOHCAHTOA, which we know and love. And we're just flipping it to find the angle instead, right? But we're not actually solving for the angle. This is technically an exact answer. Right? Let's do a slightly different one. Okay. Here things get amped up a bit. So if you have, okay, this looks nasty, but what you're going to remember is that, okay, if I let theta be some inverse sine, for example, right, and I have the values on the triangle, right, in this case, I have cos inverse of 5 over 13. This actually tells me the lengths of some of the sides of my triangle, which means I'll be able to complete the triangle by finding the last remaining side. If I have 2, I need 3, right? So I need to find the missing side. And what you're going to do is you're going to say, okay, I'm going to let theta be cos inverse of 5 over 13. Okay, that's the same as what we did here, except now I'm told that the cos inverse is 5 over 13, so adjacent over hypotenuse. So I have 5 over 13, okay, and then I need to solve for this side. Okay, so from here, right, I'm just going to draw some triangle. I don't typically care if, you know, maybe I'll just use a little bit nicer looking triangle. That's a right angle, if you can believe it. Yeah. Not bad. But what I'm going to do is I'm going to put theta down here. And if I'm told that the inverse cosine of 5 over 13 is theta, well, the cosine is adjacent over hypotenuse. And so the adjacent is 5 and the hypotenuse is 13. Okay. They've given us this triangle to fill in, so maybe I'll just transfer it in here. Maybe I shouldn't even have drawn mine. Okay, so this is 5 and this is 13 from, oops, cos of theta is the adjacent over hypotenuse. Okay. So then if theta is the cos inverse of the adjacent over the hypotenuse, then if cos inverse of 5 over 13 is my theta, right, then the adjacent is 5 and 13 is my my hypotenuse. I can find the opposite, right, just using the Pythagorean theorem. We find the length of the missing side using the Pythagorean theorem. a squared plus b squared equals c squared, where c, of course, has to be the hypotenuse. And a and b can be used interchangeably for the opposite and the adjacent. And so what we have is we have 5 squared plus b squared, right? This is my b. Hard to make it not look like a 6. I don't know. Okay, so I have 5 squared plus b squared is 13 squared. I can solve for b really easily. 5 squared plus b squared is 13 squared. Use your calculator, right? 13 squared is 169. 5 squared is 25 plus b squared is 169. So minus 25 from both sides, I get b squared is 144. I square root that. Plus minus when I take the square root. But because the sides have to be positive, right? We can't have a negative length, but can't have a negative length. So b then is the square root of 144, which is 12. So here, now we know that b equals 12. So I use this inside portion to fill in my triangle, and then I'm just going to take the sine of, remember I let the angle be cos inverse of 5 over 13. So now I want to take the sine of theta. Well, sine is just the opposite over hypotenuse, so 12 over 3 is your answer. From the triangle now, we now see that the sine of theta is 12 over 13, opposite over hypotenuse. Okay, so it looks hard, but it's actually not. It's potentially the easiest trig thing we've done because it's just drawing on stuff that we already knew, right? Pythagorean theorem and SOHCAHTOA. Okay, so let's see here. We can solve some of these guys. Find the exact value of the expression, right? So that means I don't want to see any decimal approximations. Let's see here. We can do 29 first, and then probably 31 because it's got a secant. Right, so this is why I brought in those the SOHCAHTOA 2.0, right? Because once we have the triangle set up, then if you go back to the beginning of our notes here, or from last day rather, right? I know the secant of theta is the hypotenuse over the adjacent, right? And so here, I'm just going to copy this and bring it down so I don't have to scroll around so much. What? Right, so for things involving secant, cosecant, and cotangent, right? Maybe we don't know those as well, but they're on here. Or you can remember which ones they're the flipped version of. But but with this table, right, this one's easy to do. But we'll start with 29 and then we'll get to, we'll do 31 after. So we've got the cos of the sine inverse of 4 over 5. So how I'm going to do this, kind of methodically, is I'm going to let theta be sine inverse of 4 over 5. So let theta be the sine inverse of 4 over 5. This is how we're going to find the triangle, right? And so that means that sine theta, sine of theta is 4 over 5, right? I can move this sine inverse over to the left-hand side, and that just makes it sine. So sine theta is 4 over 5. So I can set up my triangle, and you can just make any right triangle. Usually I'll put theta down here. So the sine of theta is 4 over 5. So the opposite over hypotenuse 4 and 5. Okay. So then I need to solve for this length. Let's call it b, right? A squared plus b squared equals c squared. Solve for the missing side. Four squared plus b squared equals 5 squared. So we have b squared is 25 minus 16. Oops. Is 9. So b squared is 9. So b is going to be 3, right? Because it has to be positive. And so I'm actually skipping the plus minus because it has to be positive. So the length of the missing side is 3. Okay. So now I go back to my problem, right? And I said, okay, well here, theta is just going to take the place here of sine inverse of 4 over 5. So now I just need to find cos of theta. Now find cos of theta. Cos theta is adjacent over hypotenuse, which is just 3 over 5. So that's the exact value. This is the exact value of the expression. Not bad, right? Okay, so let's see here. Let's do another one. Like I said, let's do 31 on here. Well, we did 29. Let's do 31. So now we're going to do the secant of sine inverse of 12 over 13. So it's the secant of sine inverse of 12 over 13. So again, I'm going to replace this with theta, sine inverse of 12 over 13. So I let theta be sine inverse of 12 over 13. So then sine of theta is 12 over 13, which I can draw on my triangle here. If I let this be theta, then the opposite is 12 and the hypotenuse is 13. So now I need to solve for the missing side. Sure, I'll use a squared because my b's look like sixes, so maybe I should be using a squared. Plus 12 squared is 13 squared. 13 squared is 169 minus 144. So a squared is 25. So a is a length of 5. So now, from theta, right, I want to take the secant of this theta, and I know the adjacent, the opposite, and the hypotenuse. So now I just need to remember what secant is. Well, from the table, we know that the secant of theta, let's see here, where did I put it? The secant of theta is the hypotenuse over adjacent. Now I just need to plug those in. Is the hypotenuse over the adjacent. So secant of theta is 13 over 5. And that's it. Okay. Let's just do one more for good measure. Let's do 34. We want to find the cotangent of sine inverse of 2 over 3. Yeah. So I let theta be sine inverse of 2 over 3. So sine theta must be 2 over 3. I can set up my triangle here. Oops. Sine theta, oops, getting sloppy. Sine theta is the opposite over hypotenuse, so the opposite is 2 and the hypotenuse is 3. And here I'm going to solve for a. So a squared plus 2 squared is 3 squared. So a squared plus 4 is 9. A squared is 5. And that's okay. So a is the root of 5, right? Because it has to be positive. We can have roots here. Oops, it's just not as fun. Okay. So now I want to find the cotangent, right? This I used to set up my triangle. Now I need to find the cotangent of theta, right? Because I'm replacing this inside portion with theta. And so the cotangent of theta from the table, I'm just going to steal it. Is the adjacent over the hypotenuse. So the cotangent of theta is the adjacent, which is root 5, over the opposite, which is 2. And I'm just going to leave it like that. Okay. You did it. So that concludes all our material. Womp womp. I know. But it's nice when we end on something that looks really complicated like this, the cotangent of sine inverse of 2 over 3, but then it's actually pretty fun and easy. That concludes the material for this course. Woo. Are there any questions? There will be a review sheet. I just don't have it set up yet because I wasn't sure how far we would get and how much to emphasize stuff. But yeah, there will be a review sheet, and we can even set up a review day if you would like. Just let me know when. I'll put some suggestions up on Moodle and maybe send out an email, because our final's not until the 16th, so we've got a little bit of time. Oh, that's what it was. I'll post a trig assignment just with everything, because it was hard to break it up because everything just kind of feeds into basically what we did today. So I'll post an assignment. It'll just be one trig assignment. How about a little bit bigger than usual, of course. But yeah, I'll post an assignment. Awesome. Okay, I'll stick around if there are any questions, but I'll stop the recording. But otherwise, it's been a pleasure having you. I'll see you for the final and a review day. Let's aim for a review day. And yeah, have a good weekend.